All right, ladies and gentlemen. So your AP test is next week. It's actually a week from yesterday, as of the recording of this video. So we're gonna talk about one more thing, this like physics related, and then early next week I'm gonna post some stuff, a video of how to log into the AP stuff. Like, kind of what you should be expecting for logging in. And, like, I'm sure some of you have AP tests before this. But I'm going to just repost some resources and probably try and make a video about how to log in and what to expect that day, I guess. So, yeah, just like general information you need. So, watch out for that. Yeah, cool. All right. So, let's talk about labs and experiments. So here's kind of the demo question we're going to be trying to answer, and we're going to flop between some of these pages. So we want to find the coefficient of friction of a piece of wood sliding on a lab table. Like that's the prompt, right? They're like, oh, you got 15 minutes. That's where 7 points go. Okay. So we're not gonna do this in 15 minutes. Watch. This video is probably be like what, 40 minutes, an hour, and then you guys are gonna all look right now, and it's gonna be like 10 minutes. Watch. Okay. So we're trying to answer this question. So before we jump into trying to answer this question and like labs and stuff in general, let's talk about like what stuff you would probably find in a physics lab, so that you're not like, oh, I would take a nuclear reactor and then rub it on the frictiometer, because you're not, one of those you're not going to find in my classroom, and the other thing doesn't exist. Which one's which, though? No, I'm just kidding. Okay, so let's talk about what's in a physics classroom. Typically, keep in mind that half of the stuff, like I have some of these things and you've never seen them because like they're older than your parents, right? Okay, so common lab equipment. We have meter sticks. We've had sword fights with those before. They are good at measuring lengths of stuff. Here, good at finding x values, right? It's like positions, lengths, things like. Ooh, my shucks. Hang on, sorry, my camera's falling. I'm a professional YouTuber, you guys. I swear. Okay. Okay. Too bad we do it live. All right. Triple beam balance. You guys know this from chemistry. This is good for masses. All right. If you want to know like how heavy something is, you need to find its mass and multiply by g, right? Because weight equals mass times g. So this thing gives us the mass. Okay. This thing will give us distance or lengths. And it probably measures things in like meters or centimeters or whatever you like. You can get it in grams or kilograms if you know how to convert. Okay, just say measure it and record your answer in meters, right? Like a normal physics student is smart enough to say if it's 56 centimeters, then it's 0.56 meters, right? Most regular physics students are that smart. Some physics students are not, but you get to assume you are. Okay. Motion detector. Please don't just say measure the distance. You have to say, and what do you record it? What units do you use? You should say what you recorded in. Motion detectors. This is the thing that I had you guys like hold up the whiteboard and like run at. And you're like, oh, look, I made a graph on the board, right? So this thing can measure a couple of different things. It can measure, best is position, right? Right. It can tell you how far away from this thing are you. Oh, dang. What's crazy is that's like plastic. It's got a guard there. See that? So this thing's just going to wipe off. So I'm just going to get it on my finger now before I see. Not like that. Pink. Anyway, it'll tell us position. It can also tell you velocities, though. Like, it can take slopes for you of its own position graph and tell you the velocity graphs. So, this thing is really good at telling you how far away stuff is and how fast stuff is going. Because it'll give you a graph of velocity, you can just look at the slopes to get acceleration. Okay, so this motion detector can tell you the three like super important kinematic variables. It'll also give you times, right? It'll give you like a position versus time graph, a velocity versus time graph, probably an acceleration versus time graph. Okay, you can assume you have tape at your disposal. Like, it doesn't measure anything, but it's made of tape. So you have it, it's available, you can tape stuff down. You can kind of use it like a meter stick. Like, you could, like, you know, lay out some tape and then like put little tick marks on it with a meter stick. That way, if you have to like bend it or something, that's easier than meter sticks sometimes. You have tape. Don't forget you have tape. You also have string. You get to assume massless. You can, like, if you use a little bit of string, be like, well, we're using 500 grams of metal mass. This 1 gram string is small enough that we're going to ignore it. Or you could just measure it, right? You could take the triple beam balance and measure your string so you know the mass of it. So you could include it. Okay. So these are just like household items you have. You also have other like household items. Most physics classrooms probably have like a microwave or a toaster to heat things up. Most of them, you can assume you have most chemistry stuff too, like beakers. Don't assume I have like acids or LSD or anything like that, right? Like, I don't have chemicals, but I do have beakers and stuff. If I really need them, I can borrow them, right? So those are things. Here are two things that I want to talk about that we have not seen in my classroom because I don't have them. I sort of have them, but they probably don't look like this. And I have them, but they're literally older than I am, so you can't get good data from them. Okay. A force gauge is exactly what it sounds like. It tells you how hard a push or pull is, right? So you've seen these in my classroom, but they don't look like a box with a little hook on them. They sort of do actually. They look like this, right? They look like a spring scale. So spring scales are kind of force gauges, except spring scales you can only kind of like pull them. You can't push on them. Some force gauges you can get push force gauges. That's kind of what like scales are. Like if you pick up your bathroom scale and you like squeeze it really hard, like it'll like, you can grab it and you're like, oh, my hands weigh 50 pounds. It's measuring the force of you squeezing it. That's a push force gauge. You're pushing on the scale. So you can have force gauges that do push and pull. So you can assume you have a force gauge. This thing will tell you forces in newtons. You could get it in pounds or whatever you want, but use newtons because that's how physics is done. You can kind of infer mass too from these things. A lot of spring scales tell you masses because what they want you to do is that's not what fish look like. Anyway. Right, you hang your fish on it, and it's like this fish weighs 500 grams. It's a tiny fish, it's like a little tuna, right? Or no, tuna are actually gigantic. It's like a little sardine, right? Hang your thing on there, so it'll say like 50 grams. It's saying that's the weight or the mass that would. It's this much weight would be caused by this much mass. So like if this were 1 kilogram, this thing will say 1 kilo, 1 kg. But 1 kilogram times 10 meters per second squared, because, you know, weight is mass times gravity, would be 10 newtons. So whatever the force is, you can just divide it by 10, and that'll tell you the weight as long as it's just like hanging on the force gauge. So yeah, so you can assume you have force gauges too. So if you're like, I want to know how hard this thing is pulling, I want to know how much tension's in this rope, if you just put a force gauge on it, it'll tell you the tension. Things like that. Cool. Okay. The last thing is a Photogate. So these Photogates are like little, they look like this. I mean, I'm a great artist, right? Of course. They have little lasers, and what happens is something goes through them and it'll block the laser, and then it'll record that this thing was blocked. So it's like, it records on or off. Can I see my laser or not? So when it goes through, it goes, I'm blocked, start a timer. And then when it goes through this one, it says, the thing blocked me now, stop the timer, and it'll tell you how long it took to go from here to here. Okay. So you can use this thing as a timer. That's what it's really good at. Because you know this distance, you can use it to get average velocity, because it's just change in distance over change in time. So you can use it to get average velocities too. That's what it's also pretty good at. So those are really the two reasons you would want to use a Photogate. If you put them really close together, you can get almost an instantaneous velocity, like the velocity right now. So you could, if you stuck them close together, that would be a good approximation. So if you want the velocity right now of something, probably motion detector. This is like a police radar gun, basically. It's a speed detector, a motion detector is probably your best option, unless the thing is really small. These don't work super good on small things. So then you use this, and you just say, take the distance they are apart, divide by how long the timer says, and then that's your average velocity. Okay, so that's just kind of lab equipment. This stuff you should be kind of familiar with. Meter sticks, you use them all the time. They're rulers, right? Mass, it's triple beam balance, you weigh stuff. Motion detector tells you how far away you are, how fast you're going, and your acceleration. Tape is made of tape. You can stick stuff together. String, you can tie things together. Make sure you say it's light. Force gauges, they measure how hard you push or pull stuff. And then Photogates are good for timers, and you can use them to find average velocity. Okay, cool. All right, so now let's go back to the question we're trying to answer in this video, right? We want to find the coefficient of friction for a piece of wood sliding on a lab table. So let's kind of picture what we've got. We've got our lab table, right? And then we've got a little piece of wood on that, right? Looks like a block. Anyway, so this thing's gonna be sliding there, and we want to figure out the friction. The important thing in this question here is that this says sliding. So now think to yourself, friction, sliding friction. We have two frictions, kinetic and static. Which one is it? Right, think to yourself, you should be hearing like the Jeopardy theme song. Do 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 do. Right? Now forget I ever did that. Erase that from your memory. I know you're gonna have PTSD. This is kinetic friction. So here's our situation. Kinetic friction, I kind of identified from the question. Friction, sliding, kinetic friction. Let's look at the equation for that. Kinetic friction is equal to our coefficient of static friction times the normal force acting on between the surface, like how hard they're pressing on each other. Okay. So now, where do we want to go from here, right? Like, let's say you figured this out, right? You're like, friction, Barton said find an equation. I'm stuck. Okay. We need to figure out how to ask ourselves some questions, right? So ask yourself a question. Why do I care about friction? I don't know. Because Barton said so. Okay. Ask yourself, what is friction? Friction is a force. Ooh, okay. So friction is a force. Maybe I should draw a force diagram. I said force. I don't know what else to do. Let's draw a force diagram for the block. Okay. Here's our table. Here's our block. All right, there you go. Beautiful block. Force, ooh, that doesn't go in there. I just put the wrong cap on the wrong pen. Okay, force diagram for this. It's sliding. Okay, well, all right, let's put the easy baby forces on first. It's got weight. It's got normal force. Oh, that's important. That's in the equation for the thing they're talking about that I'm trying to find. I'm trying to find this coefficient of friction. What is that thing? Okay, well, there's one of the things that's in the equation I probably want. Okay, let's see. I'm going to say it's sliding to the right. So let's see. If it's going to go to the right, I probably have some kind of force applied. And then I have my friction kinetic going backwards. Okay. I know that the normal force and the weight have to be the same because it's sliding across the table. It's not going up or down. It's staying at the same height. So if it's at the same height, its velocity is 0 and acceleration 0. So I know the forces in the y direction are balanced. Okay, cool. Now, let's see. Force applied equals friction kinetic. We don't know the force applied though. All right, we do have this equation though. Force or friction kinetic equals our coefficient of friction times the normal force. So what do we need to figure out here? That's what you should be asking from here, right? What do I know? And what do I need? Right, we're not gonna figure stuff out so much as we're just gonna measure them, right? What do I need to measure? Okay. So we know that our normal force is equal to our weight. We should probably write that down so we don't forget it. And I know weight equals mg. Okay. So do I know my normal force? It's going to be important because it's in the equation with kinetic friction. Do I know my normal force? Well, do I know my weight? Do I know my mass? No. But thank goodness we live in 2020 and triple beam balances exist. So we can just measure the mass. So we're going to weigh our block with a triple beam balance. So let's write that down somewhere. Let's see. Weigh block with triple beam balance, TBB. Don't write that on the AP test. Write it out. But here, we'll maybe put procedure. There you go, just in case. Because on the AP test, they'll probably say, how would you measure this, right? Write a procedure for how a regular physics student could measure this. That's almost guaranteed going to be a question. I don't know what you're going to be measuring, but okay. Sweet. So we can measure our mass. Let's go back to this because this is a lab, right? We want to find the coefficient of friction for a piece of wood sliding on a lab table. Okay. And when we say find, we mean measure. Measure, this is a bad question by me. We should put measure. Or maybe determine. I think determine's what the AP test will probably say. Okay, so we're trying to determine this value. What that means is we need to make a graph. Every time they're asking you to do an experiment, they want you to make a graph. You're going to measure some variables, you're going to put them on a graph, and then you're going to look at the slope. Our goal here is look at the slope of a graph. So when we are looking for a graphical barn, I don't even know what to graph. You are skipping back and forth between stuff. First we've got lab tables, then we have equipment. Okay, breathe. We want to figure out how sticky the things are between them. Okay, we found this formula. We said, all right, this is important. It's the formula that involves the thing we're talking about. Okay, I want this. I'm trying to make a graph. Okay, you're doing great so far. Look at that. So if I want to make a graph out of this thing, we want to relate this to y equals mx plus b, right? We don't have a y-intercept, so that's good. That's not going to be there. This is telling us what to graph and where to look for the thing we're looking for. Y is going to be our dependent variable. This is going to be the thing we're going to measure. M, this is our desired value. We want the thing we're looking for to be the slope. I'm going to just put target here. The thing you're looking for should be the slope. And then X, that's going to be your independent variable. That's the thing you change and measure. Okay? So because of the way these equations are set up, we want our normal force, which is actually the weight. We could maybe substitute it for the weight, to be our independent variable. And we want our force of friction to be the dependent variable. Okay. So how are we going to measure the force of friction? And then how are we going to measure the normal force? The normal force is equal to the weight. Actually, let's back up. Let's make a graph first for what we're trying to do here. And then we'll figure out how do I measure it. Okay. I'm trying to graph this. This is by itself. That's my dependent variable. That's going to go on the y-axis. So we're going to put on our y-axis, this is going to be our force of friction kinetic. On the x-axis, that's our independent variable. That's going to be our normal force. And we might cross this out and change it later to something else that's easier to measure, but it has to represent the normal force. Okay. Then we're going to graph this. There's no exponents or fractions or anything weird here. So we're going to get a linear graph. And then this is the m. This is the slope of that graph. So we are looking for what is the slope of a friction versus normal force graph to figure out our coefficient of friction. I'm going to go back and give you some more examples of how to set these up in a little bit, but let's finish the actual question example, right? Okay, so I can't measure normal force, right? I don't have you could maybe stick a force gauge in between your two surfaces. Like if you had the block, no, that wouldn't work even. So block, force gauge. Okay, so if you had this, you can't use the force gauge to measure this normal force in between them, because now the force gauge is the thing being dragged across the table, and now it's the friction between the force gauge and the table, not between the block and the table. So we can't, there's not a thing to measure normal forces, right? You have to measure something else and infer the normal force. So our normal force is equal to our weight. We can measure the weights of things, right? Like weighing machines exist. So we are not going to graph our normal force. We're going to graph our weight instead. We're going to make a substitution. Because these two things are equal, we're going to take the weight and we're going to substitute it in there. Okay. So now the equation we're working with is this. Yep. Okay. So we're still going to measure our force of friction, and instead of that should be a W. Okay. Instead of measuring the normal force, we're going to measure the weight. Okay. So weight is mass times gravity. So we're going to change the weight of this thing. We are going to change the weight of our block and then measure and then figure out how much force it takes to make it slide, right? Okay, wonderful. So now let's talk about how we would actually set up our experiment. Let me get another blank piece of paper because I'm running out of room here. So we need to measure the weights of this thing. So what we're going to do is we're going to measure the weight of the block, and then we'll just put like little weights on top of it, right? So we'll increase the weight. We'll just make it heavier, and then we'll slide that. Okay, so you're going to slide it. You're going to have your block. We'll slide it across, and then we'll measure how much force. We'll put a force gauge on this thing. All right, hook it on there. We'll pull it at constant velocity so that, where's my force diagram? There it is. If we look at our force diagram, my force applied, the pulling force that's making this thing slide, so the force gauge, if it's equal to this, to my force kinetic, then if I know the applied force, then I know my force of kinetic friction. So if I just stick a force gauge and pull this at constant velocity so that they're balanced, so that they are equal, then you can just read off your force gauge, and that's actually telling you the kinetic friction so that they're balanced. Okay, so hook a force gauge on here, pull this at constant velocity, and you could hook up like a motion detector over there on that side just to make sure you're going constant velocity. That's pretty tough, but you can try your best. And then you have your force of friction, right? You just record this number right here. And then you have your weight, because we can weigh the block with the little masses on top of them, right? So then you graph those. So here's your force of friction that we read off our force gauge, and then here is our sorry, not mass, our weight that we know by just weighing these blocks, and then this slope will tell us the thing. That way you're not just finding like, yes, you could do this one time. The smart kid's always like, Barton, couldn't I just find the weight of the block once and do this, and then ta-da, there it is. The point of doing the experiment is when you make them on there, because they're not all going to perfectly line up, because, you know, physics doesn't work in real life. This best fit line takes an average, so you're not doing words. You're not just doing it one time and then getting one number. This way you're doing it multiple times with multiple weights to get your slope. This takes an average and just gives you a better value. Okay. And then the slope, obviously, you just slope formula, like m equals change in y over change in x, and then that'll get you your slope for there. Okay, so that would be your coefficient of friction, coefficient of friction, not static, it's kinetic, it's moving. Okay, we need to figure out what are the units for this thing now. Your units, I gotta hang on, condense. There we go. I gotta focus myself. Okay, units for slope. Are your y units over your x units. Okay, so the force of friction, it's a force, so its units are going to be in newtons. Weight, that's the force of gravity, so it's also in newtons. So in this case, newtons over newtons cancels, so our coefficient of friction is unitless. That's true. Coefficients of friction are unitless. It's just a ratio of how much of the weight is transferred into like sideways resistance. So it's unitless, which makes sense. But this is how you find your units of your slope. Okay, so we answered the question. We're half an hour in. What did I say? Easy peasy 10-minute video. Okay. Now that you're all super overwhelmed, breathe. Breathe in and out. You're fine. Okay. One more page, hopefully, of me yelling at you guys and telling you how to do physics, and then we're done with notes for the week. Okay. So let's talk about how to think when you're graphing, because that whole thing was super complex, right? So let me give you another situation. Let's talk about something pretty similar to what we were just looking at, but let's look at this thing called an Atwood machine. Okay. So the idea here is you have a little cart and it's got like really nice bougie bearings so that there's not any friction in them. And then it goes over this pulley to a hook where you can add some masses onto there. And then you let this thing go. So, or you can put a constant mass and add mass to this, make the cart heavier. We'll do the cart heavier. Let's put mass on the cart because I don't have nice masses that you can add mass to. So we'll put mass in the cart, right? We'll put little blocks to make it heavier. So we want to know, what is the relationship between the motion of this cart and the mass of the cart, right? So we have a constant force pulling. This thing is going to be the same force every time. However much weight this thing has, that's the force driving the system. So our force for the system is constant. What do we know about a force driving a mass? What's a force going to do to a mass? It's going to accelerate it, right? So the first thing we do is we look at our system, try and figure out what's going on and relate that to a equation. So I say, I want to know, how does a constant force affect a variable mass's motion? And the way we're going to measure motion for this experiment would be acceleration. Okay, so I find an equation. We want to figure out the motion, the acceleration. Okay, what's the acceleration of this object? Okay, so we look at our equation. The variable that's alone is going to be your y variable. Okay, the thing you're looking for always needs to be next to another variable. I'm looking for the acceleration. It has to be next to another variable. The variable that's next to the thing you're looking for is going to be your x-axis variable. So for us, oh wait, I did this wrong earlier. I'm a dummy. Sorry, I can't plan ahead. So for us, our force for this system, oh no, I'm a dingus. I am a dingus. I apologize, you guys. Nah, we'll do it this way. Okay, the force is gonna be constant. Oh my god, I hate myself. You know what? I think I set up the problem wrong, you guys. We'll put mass here. Okay, and we're gonna no, I hate myself. It works best if we have no, that's fine. Wow, I hate myself. All right, you guys, how to think when graphing. Back up. We might have to cut this a little bit. I might learn video editing, you guys. All right, ladies and gentlemen, I decided the example I was doing was dumb, so we're doing version 2. Let's talk about an easier example. Okay. Let's talk about, we've got a little cart. Ooh, there you go. Tailpipe, putt. Okay, we got a little cart and we want to know what's the velocity of this bad chicken. Okay. first thing we want to do is find an equation that has the variable we're looking for in it. We'll say, for argument's sake, you say the velocity equation first. V equals acceleration times time plus initial velocity. Okay, this thing's going pretty constant though. It's not speeding up and slowing down. So we'll say, for argument's sake, it's constant velocity. So its acceleration would be 0. So this thing goes away and V equals V naught. That's not helpful to us. So let's think about another equation that we know that has velocity in it. How about the position equation? X final equals 1/2 AT squared plus V naught T plus X naught. Okay. We set acceleration 0, so this will go away. So X final equals velocity initial will just be velocity because it's not changing times time. And we're going to say wherever it starts, that's 0. So that goes away. Now we have a nice linear equation that's super easy for us to graph. So we're looking for the velocity. You do want the thing you're looking for to always be the slope of the equation, right? You want it to be next to another variable. This is your y-axis, which is your dependent variable. This is your x-axis, which is your independent variable. So we're going to put position, we'll measure it in meters, and then we'll put time, we'll measure it in seconds. Okay. It's gonna go, we'll say it goes like 2 squares, then 2 squares, then 2 squares, then 2 squares, whatever. So it goes like this. Okay, there's our graph. Because this is y, and this is t, y equals mx plus b. X equals v initial t plus x initial. So the b's are gone. Our x variable is time. Our y variable is position. So our slope must be our velocity. And we know x versus t slope is v. So we're looking at the slope there. Okay. Your goal for these is whatever they're asking you to find, measure the variables around it, and then the thing you're looking for should be the slope. So let's take, for example, we want to find the acceleration of something, right? You find an equation with acceleration in it. So V final equals AT plus V initial. So you want to measure the time and the final velocity, and you want to try and make the initial velocity 0. To measure a velocity, you could probably just use like a motion detector and it'll give you a velocity graph, right? Let's say you want to measure friction or something. So we have friction static equals the coefficient of friction times the normal force. So if we're looking for this, like we were on the first example, you put your normal force on that axis and your friction on that axis, right? And we saw you might have to replace this with like weight to make it work. Let's talk about like nonlinear stuff, right? What if I want to know how much something's accelerating and I can't measure velocity well for whatever reason? So if we look at x final equals 1/2 AT squared, if I want to measure my acceleration, we can see the stuff next to it is the 1/2 and the t squared. So we want to graph that on the x-axis. You don't want to put constants like in an axis though, that's kind of weird. So we'll just graph the t squared. And then this variable, this by itself, is our y-axis. So we'll graph position versus time squared. And then our slope is the stuff that's left over. So it'll be half of our acceleration. So whatever the slope is, let's say it's 10, that's half the acceleration. So the acceleration would be times 2 would be 20, right? So whatever variable you're looking for, try and make that the slope of your graph and then find the slope. Okay. So for homework this week, obviously you guys should watch this video. You're not really going to have a like participation thingy this week. But really early next week, I'm going to post something, and you guys are going to have to do a like practice login for the AP test, and you're gonna have to send me a screenshot of it. I will post more information on that like super early next week, like probably Monday. But here is your review on graphing. So enjoy. Sorry about that little hiccup in the middle. That was a bad example. It works out, but it's like you're not gonna like it. So All right, I love you guys. Be safe. Email me if you don't like your grade. Email me.